What if our whole search for alien intelligence has been sort of stuck, limited by what we think is possible? We usually picture radio signals, maybe lasers. But what if really advanced civilizations leave something else behind, something more permanent? Today, we're really digging into something called cosmic archaeology via gravitational fossil networks. CAFEIN for short. It's a pretty revolutionary framework proposed by Mr. Shahryar Ghiasi. So our mission here is to unpack how CAFEIN imagines finding these persistent gravitational signatures left by huge engineering projects, basically treating space-time itself as this giant historical archive. And importantly, how it gets around the big problems with traditional SETI.
Yeah, it's a completely different way of thinking about it. We're shifting from, passively listening for a signal that might blink past us to actively searching, almost like archaeologists, looking for these long-lasting remnants of technology. And these gravitational effects are treated like, well, fossils in space-time. The really clever part, I think, is how it tackles the synchronicity problem.
Yeah.
It means we could potentially find evidence of a civilization, even if they existed billions of years ago, or, if we just happen to be looking at the wrong time for a signal.
That is a huge shift. So, okay, let's unpack that. Traditional SETI, it's mostly been about radio waves, optical signals, right? What are the fundamental issues with sticking just to that?
Well, yeah, a lot of traditional SETI works under what people call the Fermi-Drake paradigm, and that makes a couple of pretty big assumptions. First, that aliens would use electromagnetic signals to communicate or just, leak them. And second, that they'd be doing it when we happen to be listening. It's pretty Earth-centric, really, assuming their tech is like ours and it's fleeting. Those signals just spread out and fade. I mean, Belby and Yurkovich pointed out, I think it was 2021, that the odds of two civilizations overlapping in both space and time with compatible tech might be, well, vanishingly small. And if we're only looking for signals we would send, we could miss almost everything else.
Right, like looking for your lost keys only under the street lamp because the light's better there.
Exactly, a very human bias.
Okay, so if signals are maybe too fleeting, too specific, what's the alternative? What universal thing is CAFEIN suggesting we look for?
Well, general relativity gives us the perfect candidate. Space-time itself, its curvature. Any truly massive engineering project, think a Dyson sphere, a huge swarm of structures, maybe even a starship accelerating like crazy, has to interact with gravity. It has to warp space-time around it. And the key thing is these disturbances, these warps, they can actually persist. Or they can leave permanent imprints. There's this thing called the gravitational wave memory effect, totally different from EM signals that just poof, fade away.
So the really big idea is these fossilized technosignatures could stick around long, long after the civilization that made them is gone. That completely solves the timing problem, the synchronicity issue. It's like finding dinosaur bones, not waiting for a T-Rex to call us on the phone.
Precisely. Cosmic archaeology.
Okay, so how do we actually read these cosmic fossils? You said CAFEIN isn't just one thing, but three approaches working together. Let's start with the first one. Dark matter tomography. What's that about?
Right. So we know dark matter makes up most of the mass in galaxies and clusters. We can't see it directly, but we map it using gravitational lensing. There's a technique called weak lensing tomography. Basically, you look at thousands, millions of distant background galaxies. The gravity of all the stuff in front of them, including dark matter, slightly bends the light from those background galaxies. It shears their shapes, distorts them just a tiny bit.
Like looking through bumpy glass.
Exactly like that. And by measuring all those tiny distortions very carefully, scientists can build up a 3D map of where the mass is in the foreground. That includes the dark matter.
Okay, I follow. So how does CAFEIN use that? What are we looking for in those maps?
It uses those existing or upcoming lensing surveys to hunt for anomalies. Things in the mass map that don't look natural, like really odd concentrations or distributions of mass that you wouldn't expect from just galaxies and dark matter behaving normally. Think about some of those wilder ideas for megastructures, maybe a huge spherical shell of habitats or power collectors, or a network of artificial black holes used for propulsion, Dyson scale stuff. These things would create very specific lensing signatures. That spherical shell, it might make a kind of ring pattern in the lensing map. A bunch of orbiting objects could create ripples.
And what's really cool here, I think, is that dark matter only really cares about gravity, right? So it acts like this neutral recording medium. It doesn't matter what the aliens are made of or if they use radio waves. It's just about mass.
That's the beauty of it. It's biosignature agnostic. We're sidestepping all those assumptions about alien biology or technology choices. Mass and gravity, that's the universal language here.
Truly universal.
Yeah, so we can basically take data from surveys like Euclid, the Rubin Observatory's LSST, even Hubble and JWST, and reanalyze it with this specific goal in mind. It's kind of like how geologists look at rock layers, the strata, to read Earth's history.
Hmm.
We'd be looking for layers or structures in the mass distribution of the universe. You know those amazing Hubble pictures of galaxy clusters causing strong lensing, making arcs and multiple images?
Yeah, they're incredible.
CAFEIN is suggesting we look for similar distortions, but ones caused by configurations of mass that just don't fit any known natural astrophysical object.
Okay, so dark matter tomography gives us a kind of static picture, a map of mass. But what if we want to catch something happening, now, or detect movement? That brings us to the second pillar, quantum entangled gravity sensors, QEGS. Now this sounds seriously futuristic, like straight out of sci-fi, but you're saying it's based on real physics.
It is, yeah, though it's definitely pushing the boundaries. It's a very ambitious vision. The idea is to deploy a network of really advanced gravity sensors across, say, our solar system, maybe satellites parked at stable Lagrange points. Think of it like a gravitational nervous system spread out in space. Each sensor, each node, would measure the local curvature of spacetime incredibly precisely, using things like super-sensitive accelerometers or maybe atom interferometers.
Okay, a network of gravity detectors. But the quantum entangled part, what does that add? How does entanglement help?
Right, that's the really novel bit in the QEGS proposal. The idea is that these sensors would share quantum entanglement, that weird quantum link where particles are connected, and measuring one instantly affects the other, no matter how far apart they are.
Spooky action at a distance.
That's the one. Now, importantly, entanglement doesn't let you send information faster than light. Let's be clear on that. But what it could potentially do is allow you to perfectly synchronize and correlate the measurements from all of these distant sensors instantaneously. So you could compare readings from opposite sides of the solar system at the exact same moment, potentially allowing you to triangulate very faint, subtle gravitational anomalies much more precisely than you could otherwise.
Wow. Is this actually being worked on? Quantum gravity sensors.
Oh, yes. Quantum enhanced measurement, gravimetry, it's a very active field. There are projects like AI on Megastructures, that's a proposed atom interferometer network between the UK and US. And NASA's NIAC program funded a study called Supreme QG, looking into spaceborne quantum accelerometers. The goal there is testing GR itself to crazy precision, like 10 to the minus 20. The basic idea, which researchers like Petsy explored back in 2018, is that using quantum correlations really can push measurement precision beyond classical limits.
Okay, give me an example. Say some massive alien ship suddenly accelerates way out in the Kuiper Belt. How would this QEGS network see it differently?
So the gravitational ripple from that acceleration would spread out. Nearby QEGS sensors would register tiny coincident disturbances, maybe in their internal clocks or position measurements. Because they're entangled and perfectly correlated, you could potentially triangulate the source of that disturbance in real time or near real time. It gets around the light travel delay you'd have if you were just waiting for, say, a flash of light from its engines. Now, the engineering challenges are immense, don't get me wrong. You need incredibly stable lasers in space, ways to link these sensors optically over huge distances, and the really big one, preserving delicate quantum entanglement over those distances. That's tough.
Yeah, sounds incredibly difficult.
It is. So realistically, in the nearer term, caffeine would probably rely on just classical correlations between highly precise but not necessarily entangled atomic gravimeters. Even that kind of network could maybe detect things like intermediate mass black hole mergers.
Yeah.
QEGS with entanglement just pushes the sensitivity potentially into the realm of detecting artificial sources.
Okay, so we have the static map from tomography and the potential real-time detection with QEGS, with the third pillar. Temporal fossil analysis. This is about space-time having a memory, right? Remembering big events.
That's exactly it. Einstein's theory, general relativity, tells us that when massive things move or change, they create gravitational waves that ripple outwards. But there's a more subtle effect, too, called the gravitational wave memory. It's like, after the main wave passes, it doesn't always return space-time perfectly to how it was before. It can leave a permanent, tiny distortion, a lasting offset. Think of it like gently stretching a sheet of fabric, and it not quite springing all the way back. Lasky and colleagues showed back in 2016, for example, that if you had lots of black hole mergers happening repeatedly in one area, the memory effect would build up. It would create like a ramp in the space-time metric itself, a lasting change.
Whoa. So any really huge engineering event, building a megastructure, maybe even dismantling one, or a massive industrial process that would literally leave a permanent mark on space-time, not just a passing wave.
That's the implication, yes. A really significant redistribution of mass energy wouldn't just send out transient waves. It could also produce this persistent quasi-static shift or distortion in the local spacetime. So, in a very real sense, spacetime itself could hold a historical record, a chronicle of these major mass-moving events.
Like cosmic stratigraphy, layers of history written in gravity.
Exactly. Like geological layers preserving Earth's past, these accumulated gravitational distortions could preserve cosmic history. And maybe, just maybe, by analyzing the details of these distortions, the spectrum of curvature, its frequency, its spatial shape, we could learn something about them, perhaps even date them. A very, very low frequency distortion might signal something that happened billions of years ago. A higher frequency glitch might be much younger, maybe only millennia old.
And I bet machine learning could be a huge help here, trying to pick out and characterize these super faint complex patterns, like how it's already used for finding signals in LIGO data.
Absolutely. The potential is there. If some ancient advanced civilization really did manipulate mass on, say, galactic scales, its gravitational legacy, its ghost, could still be detectable today, long after the civilization itself is gone.
This whole framework is just
Yep.
mind-bending. So, okay, pulling it all together, how would you actually do a caffeine search? What's the practical pipeline, the step-by-step?
Right. It's envisioned as a pretty structured five-stage process. First stage is survey design. That means getting and processing the right data. We're talking large-scale lensing data from those wide-field telescopes, Euclid, Rubin, JWST, plus gravity sensor data, maybe from existing things like spacecraft navigation networks, pulsar timing arrays, and definitely future missions with atom interferometers.
So gather the data. Then what? You need to know what signals you're hunting for.
Exactly. Step 2, signal modeling. This is where you build theoretical models. What should the gravitational signature of a hypothetical Dyson sphere or an accelerating starship fleet actually look like? For the lensing part, you'd run simulations, retracing light through computer models of galaxy clusters with artificial structures embedded in them to predict the specific lensing anomalies. For the sensor network part, you'd model the space-time ripples from moving masses and simulate how the QEGS network, or even a classical one, would respond.
Got it. Model the targets. Step 3.
Detection pipeline. This is where the heavy lifting happens with the actual data. You apply sophisticated algorithms, maybe matched filtering, looking for known templates, or maybe machine learning classifiers to sift through the noise. You're looking for anything that significantly deviates from what we expect from known astrophysics. Finding the anomalies. Then, step 4, and this is absolutely crucial, validation and cross-checking. Any potential signal, any candidate, has to be scrutinized like crazy. Could it be a natural explanation for lensing? Could it just be a weird alignment of galaxies or an unusual clump of dark matter? For the temporal signals, could it be some rare but known astrophysical event, like a glitchy pulsar or an odd black hole merger? You have to try your best to rule out the natural possibilities. And a really powerful thing here would be finding a correlation between different methods. Say you see a lensing anomaly in a certain patch of sky, and the pulsar timing data from that direction shows a weird drift. That would boost confidence significantly.
So you're looking for multiple lines of evidence pointing the same way, not just one weird blip.
Precisely. Multi-messenger, but within the gravitational realm. And finally, step 5, characterization. If you actually find a credible anomaly that survives all the checks, then you try to figure out what it is. Reconstruct its properties from the data, its mass, its shape, its location from lensing,
Yeah.
or pinpoint the event in space and time from sensor network data. And then you start the very difficult process of inferring if it's more likely artificial or natural. It's a careful step-by-step process.
It really sounds like a fusion approach, pulling together lensing surveys, maybe gravitational wave detectors like LIGO Virgo Kagra, pulsar timing, future quantum sensors, each giving a different angle on this gravitational fossil network. And you touched on the scale earlier that really jumped out at me, the sheer volume of space you could search.
Yes, the potential scale advantage is kind of staggering when you think about it. Let's put some rough numbers on it. Traditional EM SETI looking for signals might realistically probe, what, maybe 10,000 stars? Mostly nearby in our galaxy? Current gravitational wave detectors. They could already be sensitive to really massive accelerating objects, maybe related to megastructures, around something like 10 to the 11 stars, a good chunk of the Milky Way. That's based on work by Sellers and others in 2022. But the big leap comes with future lensing surveys. the Vera Rubin Observatory, for instance. They could potentially map the mass distribution across billions of galaxies, effectively covering maybe 10 to the 17, even 10 to the 18 stars across a huge volume of the observable universe.
That's an almost unimaginable increase in reach, searching entire galaxies, potentially billions of them, not just nearby stars.
It's a completely different scale of search space.
Okay, this is incredibly ambitious, really pushing the frontiers. But let's be realistic. What are the biggest roadblocks, the major hurdles? And where are we right now in terms of actually being able to do this?
Yeah, absolutely. It's definitely a long-term vision, and the challenges are significant. Let's break it down. For the gravitational lensing surveys, we're getting amazing data, especially with telescopes like Euclid and Rubin coming online. But the tricky part is telling a faint technosignature apart from just really complex natural structures. Galaxy clusters are messy, cosmic filaments are complicated. Teasing out a subtle artificial signal requires incredibly high-resolution data and really, really sophisticated modeling to be sure it's not just, weird astrophysics.
Right, separating the signal from the noise of the universe itself.
Exactly. Then there's the quantum gravity sensors, QEGS. Look, building that kind of entangled network across the solar system is, well, it's a massive engineering challenge. We're making progress with atom interferometers in labs, getting down to sensitivities like 10, 11 meters too. Space-based ones are aiming for maybe 10, 14. But the biggest hurdle, hands down, is maintaining that quantum entanglement between sensors that are millions or billions of kilometers apart. That is incredibly difficult technology, likely decades away, if possible at scale.
So the full QEGS vision is maybe more aspirational for now.
I'd say so. In the near term, as I mentioned, CAFEIN would likely rely on classical correlations between unconnected but still very precise gravity sensors. That's more achievable. Then, temporal analysis looking for that gravitational wave memory. Detecting that requires either extremely strong signals, which are rare, or accumulating the signal from many, many events. Remember that calculation for LIGO needing maybe 100 black hole mergers? That tells you it's tough. It becomes more feasible with future, much more sensitive detectors, things like the Einstein telescope or Cosmic Explorer, or perhaps by focusing the search on stronger, but maybe rarer, events that happened more recently, say in the last few million years.
Okay, and what about just handling all the information?
Data analysis. The sheer volume of data from things like LSST is going to be astronomical, pardon the pun. We'll need incredibly powerful algorithms, probably heavily reliant on AI and machine learning, just to process it and flag potential anomalies. And even then, robust calibration is key to avoid being swamped by false positives. Any interesting hit would still need intense scrutiny by human experts. Which brings us back to the final, maybe biggest challenge: astrophysical mimics. How do you really know it's not just some weird, unknown natural phenomenon? The caffeine strategy has to be conservative, extremely conservative. Only a signal that genuinely has no credible natural explanation, something truly bizarre and maybe corroborated by multiple methods, could even begin to qualify as potential ETI evidence.
Extraordinary claims require extraordinary evidence.
Absolutely. And here that likely means seeing the same anomaly through different gravitational lenses, so to speak.
So it's definitely a long game, pushing science and engineering. But it feels like it's grounded in physics we understand, even if the tech is futuristic. It's not pure speculation. It's mapping out a research direction.
That's a good way to put it. The most practical parts, like reanalyzing lensing data or adapting gravitational wave surges, could happen relatively soon. The full QEGS network, that's more of a roadmap for where future quantum sensing technology might take us. But the underlying principles are solid.
This whole conversation has really shifted my perspective on SETI.
Yeah.
It feels like we're moving from just, listening by the galactic shore for a message in a bottle to actually becoming cosmic archaeologists, getting our hands dirty, metaphorically, digging for ancient artifacts buried in the structure of space-time itself.
It really does change the philosophical landscape too, doesn't it? For one thing, it kind of de-emphasizes needing reciprocity. We don't need them to be intentionally signaling us. The search becomes more like paleontology finding fossils rather than trying to have a conversation. It also forces us to challenge our ideas about life or intelligence. By looking for these huge mass-based signatures, it's fundamentally agnostic about biology or chemistry. It sidesteps our Earth-centric biases. But it also demands, I think, a certain epistemic humility. If we found something, inferring intelligence would be really indirect. It would rely on the signal being truly unique, defying all natural explanations. So any conclusion would have to be tentative, built on cumulative evidence, inherently uncertain. And what's truly mind-boggling is what it implies about timescales. If caffeine works, it could uncover evidence of civilizations that rose and fell maybe billions of years ago. It connects us to the entire sweep of cosmic history. And that, of course, raises a pretty profound question for us, doesn't it? If civilizations can exist, build on cosmic scales, and then vanish, leaving only these faint gravitational echoes. What does that tell us about the likely lifespan of any advanced technological civilization, including our own?
That is a heavy thought to end on. Imagine if one day we detect it. Not a message, not a beacon, but an ancient ripple. A monumental ghost embedded in spacetime. What would that truly tell us about our own place in this vast universe? And maybe about the ultimate fate of civilizations that reach for the stars? Something to think about. Thank you for joining us on this deep dive.